Hi everybody, today we're going to talk about acids and bases, chapter 16. So as you know from last year, we have three definitions for acids and bases. We have the Arrhenius definition, the Bronsted-Lowry definition, those we covered last year. This year we're also going to add the Lewis definition. The Lewis definition is removed from the AP exam, so we're only going to spend just a little bit on it. So we're going to start with the Arrhenius definition. This is Savante Arrhenius. He's the first to kind of study acids and bases. So the Arrhenius definition of an acid is that it's a substance that produces H plus ions in water. And we can either call them protons, hydrogen ions, or hydronium ions. Remember, hydronium ions are H3O plus. This is the same thing as an H plus with water attached to it. Acids, some of the properties, they taste sour. They're corrosive. They sting. And some examples of acids like hydrochloric acid, sulfuric acid. So hydrochloric acid, 3 molar of that is stomach acid. Sulfuric acid is car battery acid. There's all kinds of acids that are found in foods. They're all weak acids, of course. So there's like maleic acid, lactic acid. Like if you eat anything that's, most fruits and veggies have a little bit of acids in them, very weak acids, but things like vinegar, acetic acid, things like, Sour Patch Kids and the sour candies, those have, I think, maleic acid. So there's all kinds of acids in foods. Next is Arrhenius bases. So according to Savante Arrhenius, a base is a substance that produces OH minuses when you add them to water. Some of the properties, they taste bitter. Bases are corrosive, just like acids are. They also sting. They don't sting as much as acids do, but they do sting. They're slippery. And acids are found in lots of foods. So bases are found in lots of cleaning supplies. So examples would be like sodium hydroxide, which is lye. So we use sodium hydroxide and potassium hydroxide to make soap, for example. They also, lye is also Drano. If you ever had a clogged drain, you add Drano to it. That's basically sodium hydroxide. The reason why we don't add acids is because they're going to react with the metals in the plumbing. So we typically add bases to clear our clogs. They also use sodium hydroxide to peel potatoes, like an industrial company. If you buy, for example, frozen French fries or something like that, they're not going to sit there and peel it by hand. So what they do is they put the potatoes in sodium hydroxide. It's corrosive and it removes the peel. Then what they do is they add a little bit of HCl to neutralize it. So basically HCl and NaOH will form water and salt. So you peel your potatoes and you get them salted at the same time. Now in reality, H plus is really a hydrated ion. it does not exist as really H plus in water. If you have an H plus, it's going to be hydrated, which means it's going to be surrounded by a bunch of water molecules. And so in reality, H plus or even H3O plus hydronium don't really exist. In reality, it's H plus with a bunch of water molecules, like 5 or 6. And so, in reality, it's really like if there's, let's say 6 water molecules, so that would be like H13O6 plus. That's really how it exists. It's an H plus with 6 water molecules around it. But just for simplicity, we use H plus or H3O plus, to indicate the ion dissociation of the acids. Now, when you add an acid or a base to water, ionization will occur. That means that it will split into the ions. Now, remember that acids are covalent. Like, for example, HCl, hydrogen and chlorine are both non-metals, and they share electrons, so there are no ions unless you put it in water. Then it actually, something magical happens, and because of the polarity of water, it actually ionizes the acids. We have strong acids and we have weak acids. Same thing with bases. We have strong bases and weak bases. Now the strong ones, the strong acids or bases, they will dissociate nearly 100%. That means they will ionize 100%. So if you put HCl in water, it will 100% go to H plus and Cl minus. Last chapter we talked about equilibrium. This is not an equilibrium. Basically your KQ is extremely large because it almost really goes to 100%. So this is one-sided arrow because it dissociates 100%. It only goes to the right side, so it goes to H plus and Cl minus, all of it. No HCl molecules are left. So this is for HCl. If we're writing, the formula for a generic acid, you'd write HA, one arrow, 100% going to H plus, and whatever your anion is, we're representing it with A minus. So can a concentrated acid be weak? The answer is yes. So whether it's a weak acid or a strong acid, that has nothing to do with the concentration. A strong acid, so if I have HCl, that's one of my 6 strong acids, that means it's going to dissociate 100%. So whether I have 0.1 molar or 10 molar of HCl, it's going to go 100% to ions, and it's going to dissociate completely. A weak acid means that it only partially dissociates, so only a little bit of it dissociates. So vinegar, for example, acetic acid is a weak acid. If I have a really high concentration, let's say, 10 molar acetic acid, or if I even have pure acetic acid, that will not 100% dissociate. So that's what it means to have a weak versus a strong acid. So the answer is yes, a concentrated acid can be weak. So for example, acetic acid, which is the ingredient in vinegar, it's HC2H3O2, is a weak acid. So low dissociation no matter the concentration. Now on a side note, acetic acid looks like this. You have a C double bond O and then an OH and a CH3 group here. Just if you remember when we talked about organic chemistry, so what makes it acidic is this carboxylic acid group here. You have a carbon double bonded to an oxygen and then an OH. The acidic hydrogen, the hydrogen that is dissociated, when it's removed, and then you have an anion, is the one that's next to the oxygen in the OH. This is the one that leaves. So you end up with an H plus, and then you end up with this ion, which in this case is acetate, so you have a negative on the oxygen there. Just so you know, it's always the hydrogen that comes off is the one that's next to the OH. So when we say something is acidic or basic, we want to put a numeric value on it. And so we use the pH scale or the pOH scale. The pH scale is a lot more popular. So in math, P means negative log. So pH means negative log of H, which means really negative log of the H plus concentration. And so because it's a negative log, a difference in 1 pH unit is equal to 10 times the concentration. Let's write that down. Difference of 1 pH unit equals 10 times the difference in concentration. So, like we said, the pH scale measures the H plus concentration or the H3O plus concentration, same thing. So, the pH scale goes typically from 0 to 14. Now, in reality, actually, it could go above 14 and below 0. The middle, which is 7, that's neutral. So whether it's water or any other solution that has a pH of 7, that means it's neutral, which means your H plus concentration is equal to your OH minus concentration. If it has a pH of 0, that means it's very acidic, and it's probably a strong acid that can make it that extremely low pH. pH 14 would be extremely basic, so probably it has to be a strong base to get it to that high of a pH. Now remember that it's negative pH, negative log, and so because of that, the lower the number is, the higher the H plus concentration. So acids have a very high H plus concentration, so they would have a very low pH. Bases have a low H plus concentration, so they have a very high pH. Something that's between 0 and 7, that's probably either a weak acid or a strong acid at a very low concentration. Something that's between 7 and 14, that's probably a weak base or a strong base with a very, very low concentration. Now, similarly, we have the pOH scale. So the pOH scale is a measure of the OH minus concentration. So pOH is negative log of the OH minus concentration. So again, it's from 0 to 14. 7 again is neutral. And because it measures the OH minus concentration, it's flipped. So something that has a very low pH would be a strong base. Something with very high pH would be a strong acid. And then between 0 and 7, that would be a weak base or a strong base with very low concentration. From 7 to 14, that would be a weak acid or, again, a strong acid with a very low concentration. Now, water is covalent, as we all know. However, because of the strong hydrogen bonding that it has, because of its very strong polarity, it will ionize slightly. So if we have two water molecules, so H2O liquid plus H2O liquid, that very, very slightly ionizes to form H3O plus and OH minus. Or you can write it this way. You can write H2O liquid dissociates into H plus and OH minus. Again, this is a very, very low dissociation, and so your backward arrow is much bigger. Most of the water stays as covalent molecules. Very little of it will dissociate. And so if I wanted to write the KQ expression for this one here, for the dissociation of water, I would write KQ is equal to concentration of H plus times the concentration of the OH minus. Or, if you wanted to write it for this one here, you can write it as H3O plus times OH minus. Either one, it's the same thing again because H plus concentration is the same thing as the H3O plus concentration. We do not include the water in our equilibrium because it's a liquid. Because this is a special reaction, the dissociation of water, it doesn't just get KQ as the name for it, so it gets the name KW. So KW is the water dissociation constant, and it's always the same, and it's always 1.0 times 10 to the negative 14, which means that each of the H plus and the OH minus are equal, and each of them have to be 1.0 times 10 to the negative 7th molar. And so if you take negative log of that, that's going to give you 7. So that's why the pH and the pOH of water are both 7. So we just said that Kw is equal to the H plus concentration times the OH minus concentration, and it's always equal to 1.0 times 10 to the negative 14. Now, I know this says 1.01, but you can just use 1.00, that's fine. Now, remember that K, whether it's KQ or KW or KP or whatever, they change with different temperatures. So it's only a constant at a certain temperature. So this is room temperature or standard temperature. And so we typically record it for 25 Celsius. So it turns out that if you were to multiply the H plus times the OH minus concentration, you will always get 1.0 times 10 to the negative 14. This applies to any solution. Sorry, my stylus is acting up a little bit. So this will apply to any solution, not just water. If you take the H plus concentration times the OH minus concentration for an acid, a base, or a neutral solution, it's always going to be 1.0 times 10 to the negative 14. Now, if you have a neutral solution, then the H plus concentration will be equal to the OH minus concentration, just like in water. And so both of them will be 1.0 times 10 to the negative 7th molar. So that tells you that it's a neutral solution. If you have an acidic solution, like if you take an acid and put it in water, then you will get more H pluses because the acid will dissociate into H pluses. And so the H plus concentration will be larger than the OH minus concentration, and it's going to be larger than 1.0 times 10 to the negative 7th molar. If you have a basic solution, it gives off OH minuses in water, and so it'll react with the H pluses. So basically it removes some of the H pluses. So now the H plus concentration is less than the OH minus concentration, and it's less than 1.0 times 10 to the negative 7th molar. So for example, if I tell you I have a solution that is 1.0 times 10 to the negative 7th molar, and it's H plus concentration, and I ask you, is this an acid or a base? sorry. Let's change that. So let's say it's 1.0 times 10 to the negative 9th molar is its H plus concentration. Is this acidic or basic? So this number is less than this number, so that means that this is a basic solution. What if I tell you I have a solution that its OH minus concentration is equal to 2 times 10 to the negative 7th molar. Now this is OH minus concentration. And so this number is larger than the 1.0 times 10 to the negative 7th, but it's the OH minus concentration, so this means there's more OH minuses than H pluses. So this would also be a basic solution. All right, we already talked about the pH scale and the pOH scale. And so if you were to take the pH and the pOH of any solution and you add them together, you get 14. So for example, for water, its pH is 7 and its pOH is 7. So 7 plus 7 would be 14. If a substance has a pH of, let's say, 2, so it's an acidic solution, then it would have a pOH of 12, and they would total to 14. So for any solution, pH plus pOH is equal to 14. So let's do a couple of problems. First one says 0.001 moles of NaOH is dissolved in 1.0 liters of water. We want to determine the OH minus concentration, the H plus concentration, the pH, and the pOH. So first thing you want to do is determine whether your acid or base is strong or weak. So NaOH is a strong base. So what that means is that it dissociates 100%. So if I have NaOH, it's going to go 100%, just one arrow, to Na plus and OH minus. So I have 0.001 moles per liter, so 0.001 molar basically, of NaOH. Since this is a 1:1:1 ratio, then that means that this is also 0.001 moles per liter. And again, only because it dissociates 100%. You wouldn't be able to do that with a weak acid or a weak base. And again, this would be 0.001 moles per liter as well. Now, the Na plus concentration doesn't really help us in anything, but the OH minus concentration helps us, because if we know the OH minus concentration, that solves part of the question here, and from that we can calculate all the other ones. So the OH minus concentration is equal to 0.001 moles per 1 liter, so it's 0.001 molar. From that, we can find the pOH. pOH is equal to negative log of the OH minus concentration. So it's equal to negative log of 0.001, which is equal to 3. Then we can find the pH from that. So pH plus pOH, we know for any solution, is equal to 14. So pH plus 3 is equal to 14, so pH is equal to 11. And then last thing is the H plus concentration. So to find the H plus concentration, you have different ways of doing it. You can either say, use this equation right here. So the H plus times the OH minus concentration is equal to 1.0 times 10 to the negative 14. And so we have the OH minus concentration. We have this number, so we can solve for the H plus concentration. Or The other way to do it is you can say pH is equal to negative log of the H plus concentration. And so the inverse of that would be that the H plus concentration is equal to 10 to the negative pH. And so it's 10 to the negative 11, basically, or 1.0 times 10 to the negative 11 molar. Let's look at the next problem. So we have gaseous HCl, so that's a strong acid, that means it dissociates 100%, is bubbled into 5.0 times 10 to the second milliliters of water. So basically 500 milliliters of water. We're told that 0.073 grams of the gas dissolves. We want to determine the H plus, the pH, the OH minus concentration, and the POH. So first thing, we're going to convert our grams into moles of HCl. So we have 0.073 grams of HCl. 1 mole of HCl is 36.5 grams of HCl. And so that gives us 0.0040 molar. And we know that this is a strong acid, so HCl 100% dissociates into H plus and Cl minus. So we know that if we have 0.0040 molar, moles, not molar, I should say moles, of the HCl, then we have 0.0040 moles of the H plus and of the Cl minus, but what we care about is the H plus here. So then the H plus concentration would be equal to 0.0040 moles divided by, we're told that we have 500 milliliters, which is basically 0.5 liters. And so the H plus concentration is oh, I'm so sorry. The 0.0, I wasn't looking at my numbers here. The 0.073 grams divided by 36.5, that actually gives you 0.002 moles. So those are 2, so this is 2 right here. And so that answer is 0.0040 molar. In my notes, I kind of did the 2 steps together. I apologize about that. So that's my answer for the H plus concentration here. All right, next I can find my pH. So my pH is equal to negative log of the H plus concentration. So that is equal to negative log of 0.0040. And so that is equal to 2.40. Just a quick note about sig figs. Because the pH is a base 10, with sig figs, if your concentration is 2 sig figs, the pH would be 3 sig figs. Those are the correct sig figs. But remember, on the AP exam, and on my test as well, I'm going to go with plus or minus 1 sig fig. All right, next let's find the POH. We know that pH plus POH is equal to 14. So that means that POH would be equal to 14 minus 2.40, which is equal to 11.6. Another note about sig figs, this 14 is actually 14.00, so don't worry about the sig figs with that. All right, last bit here is, let's see, the OH minus concentration. So the OH minus concentration you can do it in two ways. You can say the H plus times the OH minus concentrations are equal to 1.0 times 10 to the negative 14. Solve it that way. Or you can say that POH is equal to negative log of the OH minus concentration. So the inverse of that would be that the OH minus concentration is equal to 10 to the negative of POH. So that is equal to 10 to the negative 11.6. And so when you punch that into your calculator, you get 2.5 times 10 to the negative 12 molar. Next problem, we have 0.001 molar of barium hydroxide. We want to determine the pH and the POH. So again, barium hydroxide is a strong base. So we know that BaOH2 is going to 100% dissociate into Ba2 plus and 2OH minus. Now, it is important to write your dissociation equation because if you didn't, you might make a little mistake with things that are not all 1-to-1-to-1 ratio. For example, in this one, for every barium hydroxide, you have 2 OH minuses. So that means that if you have 0.001 molar of the barium hydroxide, you'd actually get 0.002 molar hydroxide ion. So let's show the work for that. I would not expect you on the test to show me the work for that. You can just, write that this is 0.002 molar here. But the more work you show me, the better, though. So let's show that. So we have 0.001 molar. That means 0.00 moles of barium hydroxide for every 1 liter. And so to find the hydroxide ion concentration, you'd say for every 1 mole of barium hydroxide, you have 2 moles OH minus. So then these cancel. You end up with 0.002 moles per liter of the OH minus concentration. Okay. Now, the reason why we find the OH minus concentration is so we can find the pH and the POH. And so it would be easier to find the POH first since this is the OH minus concentration. So you can say that POH is equal to negative log of the OH minus concentration. So it is equal to negative log of 0.002. And so that is equal to 2.70. Actually, just 2.7 if you wanted correct sig figs. And then to find the pH, you can say pH plus POH is equal to 14. So pH is equal to 14 minus 2.7. So that gives you 11.3. So let's review the strong acids. There are 6 strong acids. All the other acids, the millions and millions of other acids, mostly organic acids, are very weak. And so the strong acids, that means they dissociate 100%. So the equilibrium lies to the right side. It's almost really not an equilibrium because your KQ is basically extremely strong because they're extremely large. So there are 6 strong acids. The 6 strong acids are, we have hydrochloric acid, so HCl. We have hydrobromic acid, HBr. And we have hydroiodic acid, which is HI. So basically all the halides bonded to hydrogen except for HF, except for fluorine. Hydrofluoric acid is a weak acid. By the way, hydrofluoric acid is used to etch glass. So in your art class, if you've ever etched glass, that's what you've used. They also sell it at the stores. So HCl, HBr, HI are all strong. Also, HClO4, this is perchloric acid. Then we have nitric acid, HNO3. And then we have H2SO4. Now, sulfuric acid, H2SO4, is the only strong acid that has 2 hydrogens in it. However, only the first H is strong. Only first H is strong. What that means is only the first proton dissociates completely. The other one does not dissociate completely. So, for example, if I wanted to write the dissociation equation, so H2SO4 dissociates 100% into H plus and SO4 2 minus. This is 100% because it's a strong acid. I'm sorry, SO4 minus. So if you break this up, it dissociates, you remove an H plus, and then what you'd be left with is HSO4 minus. So then, the HSO4 minus can then dissociate to give off another H plus and SO4 2 minus, but then this proton is not strong, and so you can't really write it that way. What you have to do is do a backward arrow as well. So this is weak, not 100% dissociation. Only the first proton dissociates 100%. The second one does not dissociate 100%. So this would be a weak acid. Let's look next at the bases. And so, again, strong bases dissociate 100%. And the strong bases are all of group 1 hydroxides. Let's write that down. All group 1 hydroxides. So, for example, NaOH, LiOH, CSOH, FROH. So all of group 1 hydroxides. And then some of group 2. And depending on which textbook you look at, they will say different things. Some say all group 2. Others say only calcium hydroxide, strontium hydroxide, and then barium hydroxide. Magnesium and calcium hydroxide, some say are strong acids, some say they're not. So, for this year, we're just going to go with these. And so, unlike the acids, like H2SO4, the first H plus is the strong one, the second one is weak. In this case, both hydroxides are strong. So that means both hydroxides dissociate completely. Okay. If you have a weak acid and or a weak base, so any that we didn't just list, those dissociate considerably less than 100%, and they would require equilibrium calculations because you can't. It's not 100% completion. So if you're given the concentration of an acid, that is not the same as the concentration of the H plus, like if it was strong, because it doesn't go 100%. And so, we have to use Ka and Kb values, which we'll discuss a little bit later. Some limitations to the Arrhenius system basically is that it only works in aqueous solutions, and it's only for inorganic bases. Let's write that down. So only in aqueous systems, and only for inorganic bases. Now, the Bronsted-Lowry definition is still in aqueous systems, so that doesn't really solve the problem. The Lewis definition, though, there are organic acids and organic bases that do not require to be in water in order for them to react. However, the inorganic bases, that is solved by the Bronsted-Lowry, because something, for example, like NH3, we know that ammonia is basic. However, according to the Arrhenius definition, this is not a base because you don't have a hydroxide. And so it's not considered a base according to the Arrhenius definition. However, it has basic properties. It's slippery, it has a pH of higher than 7, it tastes bitter, and so we know that it's a base, and so there must be a better definition for acids that we can, or sorry, for bases that we can use. And so the Bronsted-Lowry solves that problem. So now we go to the Bronsted-Lowry definitions of acids and bases. Those are two different scientists, by the way, Bronsted and Lowry. So for an acid, according to the Bronsted-Lowry definition, an acid is an H plus or a proton donor. H plus is the same thing as a proton. Okay, so for example, if you have HCl and you put that in water, HCl is a proton donor. That means it donates a proton, so it gives away an H plus. So what would be left of it would be Cl minus after it gives away its proton. And then in this case, water grabbed that H plus from the HCl, and so it becomes H3O plus. So the HCl is an acid because it donated or gave away a Cl minus, or sorry, an H plus to become Cl minus when it reacted. A base is a proton acceptor. So it accepts a proton. So for example, if I have NH3 in water, notice I do a double arrow because it's a weak base, not a strong one. If it was a strong one, it would be a one-sided arrow. So a base is a proton acceptor. That means it accepts or gains a proton. So the water will give away its proton to the ammonia, so it would become NH4 plus. It accepted NH plus, and then the water would become OH minus because it gave away its proton. Another example is cyanide ion. Cyanide ion is basic. We know that because when you add it to water, it accepts a proton to become HCN, and then you have OH minus. So an acid is a proton donor, a base is a proton acceptor, according to the Bronsted-Lowry definition. Now let's go back to the Bronsted-Lowry acids. There are several types of Bronsted-Lowry acids. There are monoprotic, diprotic, and triprotic, and then we have oxy acids and organic acids. So let's start with the monoprotic. Mono means one. Protic refers to protons, so that means it only has one proton. So for example, HBr. So HBr, when it dissociates, it's a strong acid, so only one arrow. Dissociates into H plus and Br minus, and so only one proton is given off, and so that's called monoprotic. Next is diprotic. So that's di means two, so that's something that has two hydrogens in it, like H2SO4, for example. And so for H2SO4, that's a strong acid. So one arrow, it dissociates into H plus and then H SO4 minus, but then that HSO4 minus can dissociate, but this is weak, so double arrow. It can dissociate into H plus and SO4 2 minus. So total are 2 protons, although only one of them is strong. Next is triprotic acids. Triprotic means they have 3 protons. So H3PO4, for example, has 3 protons in it. So H3PO4 is a weak acid, so double arrow. Dissociates into H plus and H2PO4 minus. Then H2PO4 minus can dissociate to give off an H plus and HPO4 2 minus. And then HPO4 2 minus can dissociate to give off a third proton, and then PO4 3 minus. Oxyacids just mean that they have oxygens in them. So, for example, H2SO4 and H3PO4, both of these would be considered oxyacids because they have oxygens in them. Organic acids are the ones that have carboxylic acid groups. So if you see COOH, that's a carboxylic acid. It looks like this. You have a carbon double bonded to an oxygen and then an OH, and then this is bonded to whatever. Remember that this hydrogen is the one that is acidic, the one that's given off. Okay? So for example, acetic acid looks like this. We kind of just talked about that. So that would be weak. So you get H plus plus, then the acetate ion. So it looks like that. So the Bronsted-Lowry definition says that an acid is a proton donor, a base is a proton acceptor. So what if you have a substance like water that can do both? We call that an amphiprotic or an amphoteric substance. If you remember from like biology, amphibian means that amph means both, so an amphibian lives both on water and in land. Amphoteric or amphiprotic means both. Both an acid and a base, or a proton acceptor and a proton donor. So this means that it's capable that's an A, sorry, of donating or accepting H plus. So water is our main example here. So we looked already at these two equations before. We looked at water reacting with H2O. Water reacting with HCl. So HCl is an acid, so that means it's a proton donor. So it donates an H plus, or gives away an H plus, and so it becomes Cl minus. So then in this case, water has to accept that H plus, and so water acts as a base here. It accepts the H plus. So when water accepts the H plus, it becomes H3O plus. Now let's look at water with ammonia, which is a base. And so a base accepts a proton, and so when NH3 accepts a proton, becomes NH4 plus. And so in this case, the water has to behave like an acid. It donates an H plus, or gives away an H plus, and it becomes OH minus. So in this case, water accepts and donates H plus. It's capable of both, so we say that that is amphoteric or amphiprotic. Okay, now, according to the Bronsted-Lowry definition, we have acid-base pairs that have conjugates. So what that means is the acid has a conjugate base, the base has a conjugate acid. So let's look at this real quick. So we have HCO3 minus reacting with water to give off H3O plus and CO3 minus. So let's look at this right here, the HCO3 minus. Did it accept or donate a proton? If you look at the HCO3 minus here, the one that looks similar to it is the CO3 minus here. So going from HCO3 minus to CO3 minus, it looks like this donated or gave away an H plus to become this. So because this gave away its proton, we say this is a proton donor. So this would be our acid. And so the one that kind of looks like it, except it's missing an H plus, we say that this is the conjugate base. So those two look similar, except that the acid has an extra H plus in that pair. Now let's look at water here. Water went from H2O to H3O plus. So did it accept or donate a proton? It looks like it accepted a proton to go from H2O to H3O plus. It gained or accepted a proton. And so that means that this, because it accepted a proton, this is my base. And so the one that looks like it, except it has an extra proton, this is called the conjugate acid. So we say that these two are a pair. Acid has a conjugate base, and then these two are a pair. The base has a conjugate acid. So the acid and its conjugate base, or the base and its conjugate acid, they look exactly the same, except the acid in the pair, where it's the real acid or the conjugate acid, has an extra H plus. Let's write that down. The acid has an extra H plus than the base in a pair. Okay, let's look at the next one. We have HCN reacting with NH3 to form NH4 plus and CN minus. Now, you might be able to just look at it and tell that the HCN is an acid, because you know if it starts with an H, it's an acid. And you know that ammonia and H3 is a base, so you can right away tell that this would be your acid, this would be your base. But if it's not clear, then try to find its conjugate. So looks like this one goes with this one right here. And so in order to go from HCN to CN minus, the HCN gave away an H plus, so that means that this is the acid, and so this is the conjugate base. Let's look at the other two. These two look like they go together. So in order for ammonia to go from NH3 to NH4 plus, it looks like it accepted a proton, and so this is your base. So this is your conjugate acid. Now if you look at the pairs, this pair right here, the acid and its conjugate base, they look exactly the same, except the acid portion has an extra H plus. Same thing with the base and its conjugate acid. These two look exactly the same, except the acid has an extra H plus. Now, the reason why they're called conjugate acid and conjugate base is if you look at the reverse reaction, so going from these this way, let's look at these. NH4 plus is an acid, so gives away an H plus, donates an H plus to become NH3. this is the base. And so a base accepts a proton. So if this were to accept a proton, it becomes HCN. So it's a reverse reaction. These are the acid and base here, but then this is the acid and this is the base here. So what is the conjugate base of H2S? All right, so this confuses a lot of people. If I want the conjugate base, that means that this one is my acid, right? And so the acid gives away an H plus to become its conjugate base. So this will give away an H plus. So it becomes HS minus. This would be my conjugate base. So if you're asked for the base, the conjugate base, it should have one less H plus. Okay, the next one is asking for the conjugate acid of NO3 minus. So the acid would have an extra H plus. The acid always has an extra H plus. So anyway, if I'm asked for the conjugate acid of NO3 minus, this means that this is my base. So a base accepts a proton, so it becomes HNO3. So this is the conjugate acid. Again, if you're not sure and you answer on the test, just when you look at your answer, make sure that it makes sense. In a pair, the acid has an extra H plus. So these two look the same, except the acid has an extra H plus. Again, here, these two look the same, except the acid has an extra H plus. So the acid always has an extra H plus. When you're looking at conjugate pairs, so an acid and its conjugate base and a base and its conjugate acid, the stronger the acid, the weaker its conjugate base. So the stronger the acid, that means that it donates H plus readily. So the stronger the acid, the more readily it donates its H plus, the weaker its conjugate base. That means the less likely or less readily the base would accept a proton. So that means does not accept a proton readily. Same thing with the base and its conjugate acid. The stronger the base, so that means it accepts a proton readily. The weaker its conjugate acid, so that means does not readily donate a proton. So for example, HCl we know is a strong acid. In this case, H2O would behave as a base. That means that if HCl is a strong acid, its conjugate is going to be a weak conjugate base. And H2O here is the base, so this is my conjugate acid. For this one, here's acetic acid. This is a weak acid. Here, water is behaving as a base. There's my conjugate acid. And here's my conjugate base. The weaker the acid is, the stronger the conjugate base. And the stronger the acid is, the weaker its conjugate base. Now you notice that I have an arrow going this way and an arrow going this way here. This is a one-sided arrow because this is a strong acid. Basically, equilibrium always lies towards the weaker side. Because if you have a strong acid or a strong base, it's going to react. It's going to dissociate. so it's no longer going to be there. The weaker side does not want to react as much, so it's going to stay. And so the equilibrium in this case lies all the way 100% to the right because this is the stronger side. In this one, this is the stronger side, so it lies this way. However, this is an equilibrium, so there is an arrow going that way. It's just not as much. The equilibrium lies more that way, or the reverse side. All right, that's it for the notes today. Hope you enjoy your couple days off, and I will see you on Monday.